Hello and welcome to the 101 Earth Observation Virtual Lecture Series. This series is delivered by the Satellite Applications Catapult in partnership with WILDLABS. This lecture is about electromagnetic radiation principle. What remote sensing is measuring? Remote sensing is measuring what is called electromagnetic spectrum. And this is a concept that is fundamental in remote sensing and Earth observation. So we see this in this figure. So we've got the sun. The sun is transmitting energy in form of light. And light, it's composed by photons, which are also known as light quanta or energy quanta. Those photons, they have a particular physical property, which is called wavelength. So mainly photons, they travel in vacuum in this form. So this is a sinusoidal form. And the wavelength is the distance between two peaks. We are talking of very little, clearly, distance and measurements, so you see nanometer. But depending on this physical measurement, we can classify the light in different categories. And we see these different categories in the right part of the figure. Those are also called bands. The human eye can see only a limited portion of it, which is what it's in color there, from the violet limit to the red limit. And the bands, they have different names. So we have a blue band, a green band, a red band, and so on. There is a lot outside, actually, the visible part of the spectrum. So we've got, for example, ultraviolet, the ultraviolet part for small wavelength, or for larger wavelength, we've got like the near infrared, far infrared, also short wave, infrared, and so on. So as you see, the electromagnetic spectrum has a large part and is large and has different bands. Remote sensing sensors can capture this in almost its entirety at different bands. Why this is important? This is very important because, as we see, some of the measurements that we can capture with our sensor are very relevant in portion of the spectrum where we actually, do not see what's in there. So for example, in the infrared portion of the spectrum, we will have some applications that are actually driven and triggered only in that part of the spectrum. However, this is the most important concept of remote sensing, electromagnetic spectrum. And it's important to understand that there are different parts of the spectrum that relates to different wavelength of photons. Actually, what is important as well is the atmosphere. So most of our sensors, they fly in space. So at a certain altitude, can be 500 kilometers, can be even more than that. There are different portions of the orbits, which are called differently depending on where satellites are. But what is important is that being so far, the measurements that we have, they pass through atmospheric layers. No? So we have our Earth, where we want to measure any information, and we have our sensors. Between those, there is the atmosphere. The atmosphere has a big impact in the electromagnetic spectrum, as we see in the figure in this picture. Specifically, the energy that is reflected, it's different at the top of the atmosphere or at the bottom of the atmosphere. Generally speaking, we want to measure the bottom of the atmosphere, so we want to measure something at the Earth. And we see how the radiation, it's what we see there in yellow. There is a general decay due to some properties, but it's important to see that there are actually some windows there where we don't have any information. And those windows there, they relate to different atmospheric components. So what is important here? What's important is that remote sensing system must function within this window. So when we are building a remote sensing sensor, we obviously need to build a sensor that captures this energy, this electromagnetic spectrum properly, and doesn't function, for example, exactly only maybe in that window where we won't have information. Now again, what we are measuring. So we have in optical Earth observation the sun as main source of energy, and we have our sensor. Sun is transmitting light, which is reflected and bounced back to our sensor. The reflection and the information that comes to the sensor is directly related to what we see on ground. Let's have a look at this picture. So in this picture we have like our electromagnetic spectrum in the x-axis with all the wavelengths. So as we explained at the beginning of the spectrum, it's the visible part of it, so what we can see. But everything that is like after around 700 in this plot is not visible. In this case, it's the infrared part of the spectrum. What is important here is that, as you see, different components on ground behave differently in terms of spectral energy that is like received at our sensor. So let's have a look at few examples here. Water. Water is this blue line at the end. So as we can see, the quantity of information that comes to our sensor is really low through all the electromagnetic spectrum. So we are very low here with just a little information on the visible part. Other components, they behave differently. So we can see this as a sort of a fingerprint. So every different component, grass, concrete, red brick, sand, and so on, has its own unique fingerprint into the electromagnetic spectrum. And by capturing this properly, we can actually classify those components. And we can have information about those. An important point here is the difference between radiance and reflectance. What we measure at the sensor is the radiance. So this is the variable that it's directly measured. Again, it's how much light the instrument sees from the object being observed. This actually includes all the atmosphere and also topographical impacts. What we want to know is actually what is really happening on the surface. So we need actually to remove these additional components through some operations, which are called radiometric correction, that transform the radiance into what is called reflectance, which is the direct ratio of light leaving a target. So basically it's the property of the material being observed. Some interesting facts here. If you recall, the beginning of the spectrum reflects to the blue, green, and red colors. Actually, if by looking at how those spectral signatures are, we can understand why we see the surrounding with those colors. So let's have some examples. So let's see some examples. So let's have a look at the concrete, which is like the highest figure up there. So as you see, it's kind of flat, or it moves slightly, into the visible part of the spectrum. So that means that there is a balance. There is an equal balance, more or less, between the colors. That's why concrete appears gray in our eyes. If you look at the red brick, which is the next curve, we see how the weighting of the blue and the green is much lower than the red, which is very high. So we have like this sort of uptrend. That's why the brick is red. So that's why we see it red. So we can actually explain what we see, in our environment just by looking and just by studying the electromagnetic spectrum. What about the other technology? The other technology is called synthetic aperture radar. So this is a completely different technology because we don't have anymore the sun, which is transmitting the energy, and our sensor, which is receiving the energy that is transmitted by the sun and reflected back. In this case, the sensor itself is transmitting a signal, which is bounced on the surface and is like received back, like a bat, in this example. Now, SAR, it's a different system, clearly because of that. The good point of SAR is that it's actually weather independent. So while optical remote sensing can actually see the clouds, because we have our source of energy again, which is the light, the sun, the light passed through the atmosphere, and then we see what is coming back. So if you have clouds, we basically see the clouds. SAR works at the different part of the spectrum, works at microwaves that actually are able to penetrate the clouds, and we are able to get cloud-free imagery. We will see more about SAR in the next videos. So as I just explained, SAR operates in the microwave domain. If you look again at the electromagnetic spectrum, and we look at the plot just next to the sun picture, we are in the lower part of it. The name of the bands in this case, they're slightly different. So we don't have anymore a classification depending on the colors: blue, green, red, ultraviolet, infrared, and so on. SAR has a different terminology that depends obviously again on the wavelength, so electromagnetic spectrum. The name is its own letter. So and you see in this table here the different naming. The most used bands in synthetic aperture radar are the X band, C band, and L band. They operate at different frequencies, and while X band has a shorter wavelength, L band has a slightly larger wavelength. So we are talking in this case of centimeter of wavelengths, so which is obviously much larger than what we described before for optical data. The main information coming out from SAR remote sensing, it's called backscatter. So this is different from the radiance and the reflectance that we described before, and it comes from this concept of energy transmission and reception. So a single radar image is usually displayed in this way, like in a gray scale. And the intensity of each pixel here represents the proportion of the microwave backscatter from the area of the ground. So again, we have our system which is transmitting energy. It bounced, in this case it's an island, we see an island, and is reflected back. We see this in black and white because we have only, let's say, a one-dimensional signal. To be actually precise, the signal is composed in what we call amplitude and phase. We will see this better in the next lecture, and in this case we are focusing only on the amplitude. But this is the main information that we typically see with SAR data. Our backscatter depends on many different components and factors of what's on the ground. It depends much more on the geometry rather than maybe on the physical properties of the ground, as we have seen with optical data. So it depends on the type, on the shape, on the orientation, and so on. There is a big dependency on SAR also on the moisture content of the target area, as well as system considerations such as the incidence angle for which the wave is transmitted, so if it's transmitted with an angle, with a different angle, and so on. The main information here is called backscattering coefficient, and it's usually measured in decibel. It's also called normalized radar cross-section. We will see in the next videos several applications that use that specific data.